Welcome back, guys. In this lecture, we are going to talk about significant figures. Now, previously, when we talked about measurements in units, we introduced this concept in the context of a measurement problem involving a graduated cylinder. What we're going to do in this section is revisit that example and essentially go into more detail as to how you record significant figures and how you keep track of significant figures as you're moving through a wide range of different sorts of calculations. So as you hopefully recall from the previous lecture, any measured quantity has associated with it a certain number of so-called significant figures. And there's an agreed upon way that scientists report these measured quantities. And the basic idea we presented was that if you have more digits, there represents a greater degree of certainty in that measurement. Fewer digits is less certainty. And we have this convention that when we report any measured quantity, the first set of numbers are the certain numbers, values that we are certain of, and then there's an estimation associated with that last digit. And so last lecture we saw this example where we were trying to measure the meniscus of the liquid in this graduated cylinder. We said that, well, hey, we know it's above 4.5, something less than 4.6. So we approximated, and we discussed how there could be, some disagreement in that last approximation. For example, we said it could be 4.55 milliliters, could be 4.56 milliliters, and all of these numbers would be correct. So now I want to revisit this problem, and I'm going to change it up a little bit. Let's suppose now that we take this graduated cylinder and we take a reading and find that the meniscus is now hovering right here at the 4 milliliter mark. I want you to go ahead and pause the video and write down with the correct number of significant figures the corresponding volume for this meniscus being directly on that 4 milliliter mark. Okay, so a common answer that students will provide is simply saying 4 milliliters. It's right on the line. Why can't I just say 4 milliliters? Well, remember our convention. The last reported digit represents a degree of uncertainty in the measurement, meaning that this value could change by at least plus or minus 1, so or if not more. So basically here, by writing down just 4, all you are saying is that that volume reading is somewhere between 3 milliliters between 3 milliliters and 5 milliliters, okay? Which of course is true, but hopefully when I write it down that way and recall that convention in that uncertainty in that last reported digit, you'll see that, well, in fact, we're sort of shortchanging this measurement device. We know more information than just that single digit. So then you could come through and say, okay, well, I know it's right at that line. I don't want to put in an actual number. I'm reading it and approximating and saying, hey, it looks like it's exactly on that line. So a next logical step would be to put in a 0, right? In 4.0 milliliters. Okay, so once again, this is going to give us a range. And in this case, the range would be something like 3.9 milliliters to 4.1 milliliters, which of course brackets this little region right here, which is accurate, right? We certainly know that it's in that region. However, once again, we know a little bit more than that, right? Because we're looking at the marking at 4.0 and we're saying, hey, it's exactly at that point, 4.0. So sorry about that. So basically, if we have a meniscus that we are being able to visually identify as being directly on the 4.0, well, those are going to be certain measurements, and then our uncertainty, which I'll represent in blue here, is going to be in that second decimal place. And this is where there could be a little bit of discrepancy. We could say, well, hey, I think it's right there at 0. Somebody else could come along and say, well, I think it's a little bit above that 0 point, perhaps just by a small portion. And of course, either one of these would be correct. But the point is that when you are reporting any of these measured values, you are going to be certain, your level of certainty is going to depend on where the markings are. So in this case, the markings are in that first decimal place. So that first decimal place and all the digits before it represent certain values, and it's that last value that is estimated based on how you've mentally broken up the space between those smallest ticks that are going to represent an estimate. And so even if your estimate is zeros, we somehow need a way to keep track of that fact and keep track of those zeros. And so this is where the concept of significant figures comes in. Okay, so once again, our goal here is to preserve the precision of a measurement. And whenever we are both representing that measurement, sharing it with other scientists, other students, or when we are performing calculations with that measurement. And this process of preservation is going to be achieved using significant figures, right? So the idea behind a significant figure, and it's going to sound a little abstract here, I'm saying basically non-place-holding digits are significant figures. Sounds more complicated. Once we start looking at some examples on the next slide, that'll make a little bit more sense. But basically, any digit that's not serving as a placeholder is significant. And the greater number of significant figures you have, the greater certainty you have in the measurement. So, for example, if we just have, say, the measure at 23.5, well, that has 3 significant digits. There's 3 numerical values there. And if we add in another decimal place, 23.56, we of course have 4 significant figures. And so really the only hard part with significant figures from a student perspective is keeping track of these zeros, as we saw in that graduated cylinder volume measurement problem. So the first rule, there's going to be 4 of them, 4 rules for determining significant figures. The first rule is nice and easy to memorize. Anytime you have a number reported and it's non-zero, that digit, that non-zero digit, is always going to be significant. So all the values in pink here, they're all significant, no questions asked, okay? Now, anytime you have zeros that are interior, in other words, they are between 2 non-zero digits, for example, here and here, those zeros are going to be significant. Then, if you have leading zeros, so they're not in between 2 non-zero digits, right? They're leading, they're in front of those non-zero digits. These zeros, it turns out, are not significant. I want to do an example to drive that point home here momentarily, but these leading zeros are not significant. Now the next rule here, it's broken down into a couple pieces. So this is dealing with trailing zeros, so zeros at the end of a number. So zeros at the end of the number, basically, in order to determine whether they're significant or not significant, we need to look at the context. So if those trailing zeros are occurring after a decimal point, then they are always significant. So that we can draw our attention back to the previous example that we just wrote down. When we wrote down this measured value of 4.00 milliliters, we saw how important it was to include those zeros after the decimal place because they are the direct result of the level of certainty we have based on the markings on that measurement device. So those are absolutely significant. Now, if we have zeros before a decimal point and after a significant digit, like we have right here, because we know zeros to the right are significant, so this is effectively an interior zero. Same thing going on right here. Those zeros are also going to be significant. Now, trailing zeros before an implied decimal point, then we have some problems. If I just write out 1200, it's not clear whether or not I mean that both of those zeros are significant or none of them are significant. So you should never write a value like this. This is a no-no. What you should do instead is write the number in scientific notation, and then scientific notation naturally draws out which values are significant. So whatever numbers are showing up before the power of 10 are all significant. So here's another nice feature of scientific notation. Not only does it help us keep track of our zeros, our place, through this power of 10, expedite our calculations as a result. It also allows us to very quickly identify which numbers are significant and which aren't. So if you meant to say that neither of those two zeros are significant, it means you only have two significant figures, you'd write this. Perhaps only one of the zeros significant, in which case you'd write this guy. And of course, if they were both significant, then you'd write out the full 1.200 times 10 to the third. Okay, so let's take a quick minute here and look at an example involving rule number 3. I see a lot of confusion initially when we're covering this topic. So let's go back and to explore this example, let's recall from our SI conversion sheet that we have a definition that allows us to move between milliliters and liters. We saw that 1 milliliter is a thousandth of a liter, so 0.001 liters. And so let's suppose we take a measurement, okay, we get a measured quantity here, and we find the volume in this measurement and report it as 0.005 liters. So the question comes up, are these zeros significant? Okay. Well, you might see from our list that these are in fact leading zeros. So because they're leading zeros, we know that they are not significant. Okay, but that can be hard to remember, especially when I'm training you guys to keep track of those decimal places. I see a lot of students make mistakes and say, well, no, it's going down to 3 decimal places. I don't want to shortchange the number of decimal places, which is true if you have a significant digit over here, but we don't. Okay, so let's see why. So to see why, we're going to go ahead and use the unit conversion that we have right up top here. Okay, we are going to convert this value in liters into the corresponding volume in milliliters. So if we know that every 0.001 liter gives us a milliliter, and we have 0.005, we basically have 5 of these, that means we are going to have 5 milliliters. All right. And if you're having a hard time with those unit conversions, we're going to spend all of next lecture going into more detail on that. So basically, we're just having to multiply both sides here by 5 to carry out this conversion. So we're going to be at 5 milliliters. Now, once we get to 5 milliliters, it's very clear that we only have one sig fig. There's only one significant figure, right? So what were these zeros doing? Well, all those zeros were doing were holding the place of that numerical value, that magnitude. And that place just simply depended upon what unit we decided to represent the number in. So if you just can change units, obviously changing units doesn't have any impact on the precision of the initial measurement. Okay, and so these leading zeros here aren't significant. They're simply holding the place and are present to varying numbers depending on the specific unit you use to represent the value. So by doing a little unit conversion problem, we can see very clearly that, well, hey, we must only have one significant figure. Therefore, those leading zeros are not significant. Okay, so now let's turn our attention to another curveball that sometimes throws students off, and this is the concept of exact numbers. So I said when we're taking measurements, we have to be very careful, of course, with recording the correct number of significant digits, and depending on the measurement device, we're going to have a different number of significant digits. But it turns out that there's a very simple type of measurement that we could take that actually has no uncertainty. Okay, so this would be an example of a measurement that has an infinite number of significant figures. And so these measurements would involve so-called exact numbers. So let's say we want to identify the number of eggs that you have in your refrigerator. So if you go to your refrigerator, open up the refrigerator, and start counting eggs, you're going to come out with a number, let's say 7. Okay, so you take that measurement, 7 eggs. Now you want to think, was there uncertainty associated with that measurement? Well, assuming you didn't have any broken eggs in there, partially eaten eggs or anything like that, but you just had an egg carton with 7 intact eggs, then you were counting discrete objects, 7 of them, and so you could have equally well written out 7.0 eggs, 7.00 eggs, 7.000000, and on to infinity eggs, and have been just the same accuracy. So that 7 represents an exact number. Okay, and there's other conditions under which exact numbers are going to show up. So exact numbers are certainly going to come from counting discrete objects, like counting our eggs, for example, in the fridge. Okay, or if we're counting atoms or any sort of object. Okay, another place where we can get exact numbers is from defined quantities. So remember, we just talked about the example that if we have 1 milliliter, that is equal to 0.001 liters. Okay, this is a defined quantity. So even though if you look at this number, you might look at it and say, well, hey, that looks like there's only 1 sig fig. Just like looking at that measured egg quantity, we might say, well, hey, it looks like there's only 1 sig fig. From the context of the problem, you need to remember that this conversion factor here does not rely on any sort of measurement. It's a definition that we've agreed upon, and it is therefore exact, and therefore has an unlimited number of significant figures. Similarly, by putting eggs after this and giving you the context that I am counting eggs, we know we're talking about discrete objects, therefore we have an unlimited number of significant figures. Okay, and the last place that we're going to see exact numbers show up is at times we're going to be presenting mathematical equations that have integral numbers that are part of that equation. So one that you're perhaps all familiar with is the definition of the radius. So radius is 1/2 of the diameter, right? So this is an exact definition. So this 2 down here has an unlimited number of significant figures. Okay, so now let's use these rules that we've talked about to determine the number of significant figures for a variety of measured quantities here. So I encourage you guys to once again pause the video, try and work through these problems, use those rules on the previous slides, reference them as needed, and then watch the video continue watching the video to go through the solutions. Okay, so first up, A. We've got a number here, 0.04450. So we've got 2 different types of zeros going on here. We, of course, have 3 non-zeros, but we need to determine the total number of sig figs. We need to determine whether or not these zeros are significant or not significant. So leading zeros up here, we remember, because they are leading, they are not significant. However, the trailing zeros are. Therefore, we have a total of 4 significant figures. So let's lock that one in. So we've got a total of 4 significant figures. And you have to remember that trailing zeros are always significant, leading are not. With our next one here, we have significant for sure, and the 3 zeros in between are interior zeros. Interior zeros are always significant. So we have a total of 5 significant figures. Now with C, I'm presenting a definition. There's 10 decimeters in 1 meter. So because it's a definition, then that means this is a defined quantity. Right? There's no measurement involved. There's no measurement involved. There's agreed upon definition. There's an infinite number of significant figures. Okay. The next example down here, 1.000 times 10 to the 5th seconds. Okay. Once again, we have a measured quantity, and now because we have these zeros after the decimal place here, we know that those zeros are in fact significant because they're trailing after a decimal point. Last here we have E, where we have a set of leading zeros, a bunch of them, but all of those leading zeros are in fact not significant. They're simply placeholders. And the example I want to draw you back to, if you're having a hard time with this one, is just change the units. Okay? If we change the units, then we quickly see that we can get rid of these zeros or add more zeros, but that can't change the underlying certainty of the measurement. So there are only one significant figure here. And last, this one I told you never to write a number this way because you simply don't know how many of these zeros are significant. So we're going to answer that last one by just saying it's ambiguous. Okay. Of course, if you wanted to say that, hey, none of these zeros are significant, what you'd have to do is write this in scientific notation. So you go 1, 2, 3, 4 decimal places. So we would write 1 times 10 to the 4 meters if we want only one sig fig. If we wanted an additional one, we'd write 1.0 times 10 to the 4 meters for 2 sig figs, and on up. If they were all significant, then we'd write 0, 0, 0, 0 times 10 to the 4, and then we would be representing 5 sig figs. Okay, so never do this. Always write one of these guys in scientific notation. Okay, so now that we have the rules down for identifying the correct number of significant figures in given values, we lastly need to cover a set of rules that allow us to keep track of the correct number of significant figures as we move through a series of calculations. So the rules are different depending on the type of mathematical operation you're performing. So the first rule we're going to talk about is a rule for multiplication or division. Okay? So the rule is relatively simple. In fact, you guys all really like this rule. The result of any multiplication or division is going to carry the same number of significant figures as the factor with the fewest significant figures. So for example, if we're multiplying these three numbers together, so we have 1, 2, 3 numbers, we're multiplying them all together, you can of course plug all those numbers into the calculator and you're going to get a value like this, right? 6.7208. Now, if you look closely at each one of these terms and use our rules for significant figures, you'll see the first term has 4 sig figs, then 5, and then 2. Okay, so at the end of the day, what we're going to do is look at which one of those factors has the fewest. In this case, it's the third one that has only 2 sig figs, and that's going to determine the number of significant figures in our final answer. So we're then going to go ahead and round this value that comes out of the calculator to correctly represent 2 sig figs. So to round, you just look at that next decimal place, and we're going to keep it simple for the purposes of this introductory material, and we're just going to say if it's 5 or above, round up. If not, we'll round down. So we see a 2, we're going to round down, and we get a final answer of 6.7. And so, of course, the same sort of technique is going to hold whether it's multiplication or division. So the second example here is a division of 2 numbers. One has 5, the other has 3 sig figs. And so the number that comes out of the calculator has way too many decimal points. Never report something like this. That will make you lose points on a lab report or in that exam. What we need to do is look back and see that, hey, we only have 3 sig figs in the factor with the fewest. Therefore, the final answer here needs to be rounded off to 3 sig figs. All right, so as I said, multiplication division rule is one that students typically are very comfortable with. In fact, you get so comfortable with the multiplication division rule that you actually use it incorrectly. You actually start using it for other sorts of mathematical operations where it does not apply, namely the operations of addition and subtraction. Okay, so I need you to really draw this out and make some big, star in your notes, highlight your notes. The rule for keeping track of significant figures for addition and subtraction involves looking at the decimal place. So the result of any addition and subtraction is going to carry the same number of decimal places as the quantity with the fewest decimal places. Okay, multiplication division, we're looking at total sig figs. Addition and subtraction, we're just focusing in on the decimal places. So when you start doing this, sometimes it's nice to set up the problems as I have here, where you are lining up that decimal place, and then you can mentally or actually draw out a line to keep track of the fewest decimal places. So if I'm adding, for example, these three numbers together, we have one with 3 decimal places, 2 decimal places, and 4 decimal places. The final result should be limited to only 2 decimal places. So similarly over here, if we have a value of 5.9 subtracted off 0.221, then we are going to see a final result of 5.679. And of course, you can basically keep track of the decimal places by saying that there's only 1 decimal place in the first value, and so we're going to round accordingly. All right, so just so you have it in your notes, the rounding rule that we're going to follow for our purposes here is, basically looking at that digit past, the less needed down. So, for example, if we need to round this guy to 2 sig figs, we'd look at this third digit here and say, is it 5 or greater? If it is, then we will round up 5.4. If it is not greater, 5 or greater, then we're going to round down and get the answer of 5.3. So when you're carrying out this rounding process, it's very important that you hold off on rounding until the very end of the calculation. So this is going to be particularly important if you're confronted with a problem involving multiple rules for keeping track of significant figures. So for example, in here we are multiplying 3 terms together, but one of the terms is a subtraction of 2 numbers. So following our order of operations, we're going to carry out this subtraction, and we're going to come up with a value that looks like this, right? 0.479. Now, you don't want to round at this stage, but what you do need to do is keep track of how many of these numbers are significant, so you can use that to guide the process of getting the correct number of significant figures at the end. So here we know we have 3 decimal places and 2 decimal places, and we're doing subtraction, so we're focusing in on those decimal places, remember. So of course the answer is going to be limited to only 2 decimal places. So what I like to do is put a little line under that least significant digit. That way I can remember that, hey, this number here actually only has 2 sig figs, but I'm going to keep that 9 here for the final step, which involves a multiplication with 2 other numbers. And so the number 19.1707 that comes out of the calculator is going to be the result of keeping this 9 present. But then when I carry out the final rounding to report the correct number of sig figs in the final problem, I'm going to remember that, well, this guy has 3 sig figs, 4 sig figs, but this number really only has 2 sig figs. Therefore, our final result is only going to have 2 sig figs. Okay, so these problems here can prove a little challenging for students, so let's go ahead and end with a few more example calculations just to make sure that we're all on the same page here. So if we are multiplying or dividing, it's straightforward. All we have to do is keep track of the total number of sig figs in the factor with the fewest. So multiplication, division, straight across here, 4 different numbers coming together. We can go through and say, well, hey, we've got 3 sig figs in this guy. This one has 1, 2, 3, 4 sig figs. This guy has 1, 2, 3, 4, 5 sig figs. And this guy also has 5 sig figs. obviously the number that comes out of the calculator has way too many, so you're going to round it off, and we're going to be rounding it off to the fewest here, which is 3 sig figs. Now, turning our attention to the next example, it involves addition subtraction. Early on, I encourage you guys, if you're having trouble with it, go ahead and set it up in this way where you line up the decimal point and carry out the addition and subtractions. And remember, we're going to be focusing in on the decimal point and the number of decimal places. So we're going to look at each one of these terms, and we are going to report a final answer that has the number of decimal places equal to the factor with the fewest decimal places. So we have 3 decimal places in the first, 1 in the second, 4 in the third, and so our final answer is going to be limited to this guy, which only has 1 decimal place. And lastly, if we have a problem involving both addition, multiplication, multiplication, division, and addition, subtraction rules, then we have to follow our order of operations and don't round until the very end, but keep track of those significant digits along the way. So what I'm going to do here is carry out that subtraction, get a result, and notice that when we do the subtraction of these two numbers here, we have 4 decimal places and 2 decimal places. Therefore, the answer is only going to be significant down to 2 decimal places. But I'm going to keep that 5,5 in the trailing 5,5 there to calculate the final answer, which is shown in blue here. And then remember that there's only 2 sig figs associated with this third number, 2 sig figs here. And so once again, we're going to only have 2 sig figs in that final reported result. Okay, to summarize what we've talked about here, we presented a number of rules for identifying significant figures. So specifically, there was 4 of them, and they really center around keeping track of those zeros. And so having those rules down pat will be indispensable moving throughout the rest of the course. And of course, the variety, the vast majority of the calculations we're going to be performing are going to be multi-step, involving a lot of different measured quantities. So we also presented a set of rules for keeping track of sig figs as we move through these calculations. And we of course saw that there were different rules for multiplication division versus addition subtraction. So again, keeping those straight and getting practice with both will be essential. We also saw that there are these so-called exact numbers that have effectively an infinite number of sig figs, and they show up in 3 ways. One could be counting. All right, so we use the example of counting eggs. So if you're counting discrete objects, you have an infinite number of sig figs. The other one was a defined quantity. So if you have a definition, and we use the example of 1 milliliter is 0.001 liters, right? That is a defined quantity. There's no measurement. There's an infinite, unlimited number of sig figs associated with that. And of course, if you have integer values showing up in the context of a mathematical formula, then that too is also going to have an infinite number of significant figures. It will be an exact number as well. So those are the key things to keep in mind here. Now go ahead and open up the practice problems for carrying out these basic significant figure calculations.